So what does it mean?
Webster effect is it comes in third unit actually. It is
Okay,
we have
okay.
not covered it. Actually, we will see that in the BJT. This again it is related. We will be discussing about this high-level injection effect. It is a kind of high-level injection effect actually. I will discuss that in the third unit actually. It's not in the first unit because it is related to the minority carriage. I don't want to discuss it right now because we will discuss it later on. But it is related to heavy injection, related to BJT.
Okay, sir. Okay.
Yeah. Nidhi had an issue.
Yes, sir. Uh,
Yeah.
sir,
Yeah.
why diffusion current occurs only in semiconductor? Because of concentration gradient.
Yeah, because you cannot in metals. We cannot have localized non-uniformity in charges. The charges will be uniformly distributed. You cannot have that kind of. You cannot maintain this inhomogeneity in charges. So, because we have seen that for diffusion to occur, a concentration gradient of charges are essential. Because the moment you say diffusion, that means there has to be a concentration gradient. So here it is the charge non-uniformity or concentration gradient of charges are there. So that is can be maintained only in semiconductor, not in metals. Metals actually the bonding actually different ways one can see it. One way of seeing it is the metallic bonding. Metallic bonding is different, whereas in semiconductors you have the covalent bonding. Another ways of seeing is doping. We cannot have doping of metals to increase their conductivity. Whereas in semiconductors, we have seen that we can add impurities and increase its conductivity by creating additional uh, electrons and holes. So this spatial uh, uh, distribution of charges, non-uniformity in charges is possible only in semiconductors. So one can see it in different ways. The important thing is this concentration gradient of charges is not possible. Another way of start seeing is the relaxation time, because the relaxation time, dielectric relaxation time they talk of, that is very small for metals. So you cannot have localized charge. So there are various ways of seeing it. The one single point I would like to mention is that you cannot have concentration gradient of charges in metals, whereas in semiconductors it is possible. So that is why diffusion current is possible only in semiconductors, not in metals. Is it okay?
Yes, sir. And sir, when they ask about utility of anything, like they have asked utility of mass action, the law of mass action, then
Yeah.
what answer do they expect, sir?
See, actually, you can see that the law of mass actions gives us a way of finding out the carrier concentration. Like, because that is what in a further discussion also we'll see that finding out carrier concentration is very important in quantifying the current. Because our objective in this paper is to get the IV characteristics to find out the current or current density rather. So current density depends on the carrier concentration. So this law of mass actions gives us, because it is the product. Law of mass action says that the product of electron and hole, whether it is intrinsic or whether it is extrinsic, it is constant. So if you know one carrier constant at a given temperature, of course, the temperature has to be constant, then the product of electrons and hole concentration is a constant. That is what the law of mass action say. So this is valid for intrinsic as well as extrinsic semiconductor. So if I know one carrier concentration, say for example, if I know the majority carrier concentration is often known because of the doping density. It is approximately, the majority carrier concentration is approximately equal to the doping density. So that is what we have seen. So if I know the majority carrier concentration, that means the doping density, and then of course the Ni, the intrinsic carrier concentration of the given material at the given temperature is known, I can find out the minority carrier concentration. So that way it helps us in finding out the carrier concentration. That is the utility of the law of mass action. You got the answer?
Yes, sir.
Yeah, that is it's
And
important.
so we have studied about long base PN junction diode,
Yeah,
right?
yeah.
Okay,
No, we
sir.
are not. This that will be
Okay, sir.
covered in the towards the end of this section actually. So the yeah.
Okay, sir.
Sudha, you have an issue?
Sir, same. What is law of mass action?
Yeah. So that you it's clear. Hello.
Yes, sir.
Is it clear?
Yes, sir. Clear.
Yeah,
Yes, sir.
yeah. It is actually basically the law of mass action is essentially about the product of electron and hole concentration in a semiconductor. The product remains constant at a given temperature for a given material. See, it is for a given material for a given temperature. The product remains constant, whether it is intrinsic or whether it is extrinsic. So, if you look at to any of the handbook of semiconductors, you will see that the intrinsic air concentration of that material at that room temperature normally will be given. So that way, it is a constant actually for a given temperature for a given material. So, product is Na squared actually. So that whether and the important thing is it is valid for both intrinsic as well as extrinsic semiconductor. Yeah. Anything else? Any other questions? Which yes. Hello.
No, sir. No question, sir.
No others. These people, Nithi or Sudha.
No, sir.
Okay. Yeah. So anyway, so now let us. So what I am trying to do is because there will be a gap now for a few days actually since I am uh, planning to travel this week and then wind up the things at Kurukshetra. So there will be a small gap. So today, what I will be doing is I will be reviewing. I mean, I will be just glance through what is in store for us in the next section and uh, for you I advise you to go through the notes as well as the question papers and try to answer those at least you should be thorough with the first unit and start reading the second unit part for the time being at least 2 weeks. I mean, I'm expecting that 2 to 3 weeks I will be away. I don't think from Kurukshetra I'll be able to conduct any classes. I'll see that if it is possible. I'll try to do that, but I don't expect because there will be a lot of, net connectivity and things will be disturbed at home there. So it may not be possible. So my your work is go through all the questions and assignments I have given about related to first unit, plus the question papers, and then once you finish that, if you feel that you have still time, then you can start with the second unit so that when we start, because anyway I'm not covering in detail the first unit also. I have not gone from the examination point of view. Only thing is the examination question papers we have discussed, that's all. My approach was slightly different that way. Yeah. So now today that is what I am going to do is just quickly review the next section. What are the things we are going to cover in this? Okay, just one second. Give me 1 minute. Is it visible?
Yes, sir.
Yes, sir.
Yeah. So, the first section, what we have done is we have introduced the importance. We have studied about the semiconductor materials and its electrical properties. So, we need to understand the basic objective. We should not forget why we were doing all this thing is we are ultimately going to get electronic devices, and those devices, the IV characteristics because we are going to use those devices for making circuits with which we can make electronic systems. Our ultimate objective as an electronics engineer is make electronic systems. So that is the very first class we have seen that. So our idea is to get the IV characteristics of electronic devices. So now, because they will be used, that IV characteristics will be used in making, designing circuits, and based on circuits, you can make the electronic system. So in the first part, we have laid down the foundation for this by looking into the electrical characteristics of the semiconductor materials. We will, as we go progress, we will you will understand that how it has helped us in finding out that, because that link should be clear. It's not that in isolation we are saying something. Which all these things are related. It's like a from top to bottom kind of things. From materials, you will go to the electrical character, and from devices. That is how we are approaching this. So that is what. So then we have seen that especially we are now exclusively talking about the semiconductor materials. So one thing we have seen is there are two kinds of devices possible. It depends on the type of the mechanism of the current conduction, because we have seen that in semiconductors a little earlier also we were discussing about that uh, all conductors have drift current. That means under the influence of electric field the carriers drift and there will be a drift current. But we have seen that in semiconductors you have another mechanism of current flow at a constant temperature, that is the diffusion. So, in general, when you talk of semiconductors, you have two types of conduction mechanism involving both electrons and holes. So, we have seen that there are four components in general, four components of current. That means because you have again another important thing we have seen is you have two mobile carriers, two types of mobile carriers. One is electron and other is the holes. So and the electrons can drift or diffuse. Similarly, holes can drift or diffuse. So that way, four components of the current. But very often, thing is one of them will be dominating. It's not necessary that all the four components will be there. See, so very often we'll be neglecting the contribution due to the others. So very often we might be dealing one or two components only, either the drift current, diffusion current, or drift current due to electrons and things like that. All sort of simplification will come. But the most general case is four types of current components you can expect. So there's a very often one talk of domination of one type of conduction mechanism that we'll be seeing. So then, now today, or this section, we are going to devote to, that means the whole second unit in, as far as your paper is concerned, you are going to discuss about the diffusion current based devices. So I'm dividing the devices, semiconductor devices, into two types. One is the drift based means a drift current based devices, and the other one yes, and the other one is the diffusion current based devices. So first section, uh, I'm going to discuss diffusion current based devices. So that is thing we need to focus on, and then later on we will be seeing the drift based devices also. Both are there. So diffusion current based devices, let us see. Now the thing is how to go about it. Like we understand that for important thing to get the diffusion current is, what is the condition required for getting the diffusion current?
Concentration gradient.
Concentration
Yeah.
gradient.
Yeah, so you need to have a concentration gradient of charges. Other two mobile charges. It should be mobile charges. So then only they can diffuse, because like gas, where there is or atoms or molecules, whenever there is a concentration gradient. Even in the case of doping, also we have seen we were taking advantage of diffusion for doping the semiconductor. There, of course, the neutral atoms we were diffusing. Whereas in this case, mobile charges like electrons and holes can diffuse. So that means we need a concentration gradient for that. And now the question is how to get it. And because you need a steady current, That means you need to maintain that. Then only the diffusion current is possible. Like the way we case in the case of drift, you apply an electric field. So long as the electric field is there, you have the current flowing. The drift current will be there. Similarly, if you want a diffusion current, there are certain conditions to be met. So that means steady state diffusion current. How is it possible? So that is what one thing we will be looking into. Now let us see how to achieve that. So we have seen that all of us agree that concentration gradient of charges is a must for diffusion. Now, how to get this concentration gradient of charges? So there are two things we need to understand, that we can have uh, majority carrier concentration can be controlled by doping. One thing we have seen, while doping we can do that. Second thing is the most important thing, which is, as far as for us is concerned, it is very important, is a spatial variation of majority carriers. From as you go from surface to down, or whatever, x direction or y direction, is a direction, you can have a variation in the majority carrier, because majority carriers, we have to understand, by and large majority carrier concentration is decided by doping. Doping you can vary spatially. From that, spatial means from x equal to 0 to x, some value you can change it. At least it can vary spatially. So the majority carrier concentration, which is decided by doping density, we can change. So that means a concentration gradient of charges can be established by changing the doping density spatially. So that is what we generally do. So then that way we say that if semiconductor is inhomogeneously doped, not homogeneously, if it is inhomogeneously, that means it is a non-uniform distribution of dopant. Non-uniform distribution of dopant means non-uniform distribution of the majority carriers. Such a semiconductor is known as graded semiconductor or graded doped semiconductor. Very often, graded means a doping density is varying with x. XYZ is possible, but we are one dimension we are considering. So, and this is possible. All of you agree to that, isn't it? Any?
Yes, sir.
Yeah. So you can.
Yes, sir.
Yes. You want to say something?
नो सर,
Yeah.
बस यस सर बोला था.
Yeah. So you can spatially vary the doping density. That way, the majority carrier concentration can be changed from point to point. So that way, you can get a concentration gradient. So that is what we are doing. So for essential thing to get a diffusion current based device is you should have a graded doped semiconductor or inhomogeneously doped semiconductor. That is one thing. Now you see the extreme case of such a device. So in this extreme cases, what you do is one side you have only p-type material that is very typically known as p-n junction. I didn't want to bring in this name in the beginning. So essentially, when we talk of diffusion-based devices, they are otherwise known as p-n junction-based devices, because there one side you have a p-type, that means majority carriers are holes, and the other side you have the electrons. So one side is p-type impurities and the other side is n-type impurities. So then one thing very important thing we have to understand is it's not that we have one p-type semiconductor and other n-type semiconductor, you join together and make a p-n junction. It's never done like that. What you do is you take a simple semiconductor block. Normally there will be prior doping will be there, like whether you have taken a wafer, Czochralski or grown in court. If you take a wafer, it is normally doped either n-type or p-type. So let us say it's n-type. Earlier the bipolar technology, you had the n-type doped semiconductor. Then part of that will be doped with p-type on the top, so it will neutralize n and it become p. So that is how p, and that is the picture you should have. Never think that you are joining a p-type in the, because very often the diagrams, probably the diagram is there here, you see this diagram, it's a bit confusing. You will see that there is N type and P type. All the diagrams we show like this, but it is never done like this. So you have started with a P type material, then a part of that P type is converted to N type. It's the opposite also is possible. So that is the standard way of getting a PN junction. So it's very important to understand that we have a single block of semiconductor in which part of us p-type dopants and dominating other type n-type dominating, and then so you can, that is an extreme case of your inhomogeneity of, because one side totally p-type and the other side totally n-type. Yeah. So this is one thing. So you have this. Yeah, you see that. So this is N and P. Oh, yeah, this is the symbol which we use. These are all, you are familiar with this kind of stuff. This is the structure. Normally, we have to understand most of the time, even though we in the for our physical description discussions we use this kind of thing, but practical device will be vertical in nature. Oh, this is the kind. Is it visible? My mouse is visible, no?
Yes, sir.
Yeah, so this is the vertical structure. Normally in the planar text structure, this is the kind of structure. But we, for in our device physics discussions, we will be using this NP device or PN like this. We will be showing. But this is the actual structure. Yeah. So when we talk of this kind of PN junctions, we have two, very often come across two types of junctions. One is step or abrupt junctions, and the other one is graded. You see, this is a classic case of step junction or an abrupt junction, because there are let us try to understand what is the meaning of abrupt junction. You know what is the meaning of abrupt junction, why it is known as an abrupt junction? This is known as an abrupt junction.
Change in the concentration.
Yeah, so any PN junction there will be change in concentration, but then what is known as an abrupt
Sudden.
junction? Yeah, it is actually, you see, at this point, let us say this is x equal to 0 or something. At this point it is changing, but practically it is not possible to do that. But in device physics paper, very often we will be dealing with this kind of junctions where there is, or you, let us see this example, the middle one. You have a line and this side is N and this side is P. This type of junctions are known as an abrupt junction, abrupt PN junction. That means it is at this point, at let us say this is x equal to 0. At this point, it is abruptly changing from N to P. One, again, we need to remember that practically it is not possible to have this kind of devices. Very often we approximate some cases like this. So that is one. So again, abrupt junctions are otherwise known as step junction. So why it is known as a step junction?
Because the step signal is like 0 or
Pardon?
1. Because of the step signal, like,
Yeah, it is actually the doping density changes from N to P like a step. Because this side it will be left side it is N. See here it is N, and then there will be a step, because later on I will be showing this. Today I don't have that diagram, but you will see that doping density once you have the donor and at the x equal to 0 again, it will become P, or this side will be uh, you'll have a donor end and then you have the acceptor end. So there will be a step change. So both these things. So we can say that it is an abrupt junction, or you can say call them as the step junction, or you can say it is uniformly doped PN junction, because this side, all this, there is no spatial within N region. There is no spatial variation of the doping density. They all are uniformly doped. And similarly, in the P side, it is uniformly doped with acceptor impurities. Then we say it is a step junction or an abrupt junction. So that is one type of PN junction. And other one is graded junction. What is the meaning of graded junction? Have you heard of graded junction? Yeah. Hello.
Sir, the junction which is not abrupt. I mean,
Yeah, but then how graded? What is the meaning of graded?
graded. Sir, we cannot define
Change in
boundaries.
concentration after small steps, like I think so.
See, actually, anything not uniform that is graded. For example, marks in a class, it is graded actually. It will not be same marks throughout the class. So you'll be having some people like wide variation in the marks is possible. It may not be like in a subjective exam you won't have the same kind of mark. Whereas in this case, you see that I said this N region is uniformly doped, whereas P region, similarly P region is uniformly doped. If the doping density within N is varying with X, because this side, for example, this side is the doping density is large, and as you go towards this, if it is decreasing, or the other way is also possible, you here it is less, and then all these cases we say it is a graded dope. That means the doping density is not uniform within the N region or within the pre region. So it can be the doping density can vary linearly with X, it can be vary exponentially with X, or it can be arbitrarily varying. All these possibilities are there. So that we can. So, but very often, again, for the simplicity of discussion, we take only one case of graded doping, that is linearly graded. Linearly graded means the doping density is linearly varying with X, either decreasing linearly with X or increasing linearly with X within N region and as well as within the P region. So very often in the textbooks, you will be seeing two types of junctions. One is abrupt junction, other one is a linearly graded junction. It can we can see the cases of exponentially graded also, but most of the standard textbooks give you two types of PN junction. One is abrupt, second is the linearly graded. Again, I am not bringing in any figure for that linearly graded. Later on we'll be seeing that, because today I'm just introducing all these terminologies, so I'm not bringing any uh, diagram. So you have two types of junction. One is a step junction, and other one is a graded one, especially linearly graded. So these two junctions are often discussed in literature, or in the most of the standard textbooks you will be. And so most of the time we will be discussing about step junction, like abrupt junction or step junction. See, very often we will see that assuming that it is an abrupt junction, that is how, because it is very convenient for us to consider that. That means it is uniformly doped one side with N and other side with P. Then a lot of physics become very simple. So that way we consider these two, step junction or a linearly graded junction. So that is another thing we will be discussing in this section. Now, so okay, so we have brought in the PN junctions, and we have seen that such a PN junctions can have a diffusion current. So we have seen that again. We are going back to our first section. Currents in semiconductor depends on the mobile carrier. See, because we should not forget our basic objective. Our basic objective is to get the current voltage relationship, and then we have seen that currents in a semiconductor depends on mobile carriers concentration or its concentration gradient. In the present case, because we are considering the diffusion currents or the concentration gradient, so once we know the concentration gradient, once we know the concentration and spatial dependence, we can get the concentration gradient. That is, there is no big deal in that. So we have to go about like that. Now, so that is one thing. Now, another issue is cropping up here as compared to the first section. First section, we have seen the equilibrium condition. That means no external field applied. But we know that most of the practical situation or the applications of devices is under non-equilibrium. That means you apply an external bias. That is what the normal operation is. So we would like to know the current when you are applying a bias. It's not that in the first section we have seen in equilibrium situations. So how will you find the carrier concentration in equilibrium conditions? You remember? Yeah. So that is the deviation you are bringing in. In the first section, we have seen there also we have seen the carrier concentration. Can't I use the same carrier concentration here also? Is it possible? Hello.
No, sir. I think so. No.
So the thing is, there we have seen that using Fermi function and law of mass action, I can find out the carrier concentration. We have seen that. Okay, again, if you look back, so that is valid. The carrier concentration we have obtained there is valid for equilibrium condition. That is thermal equilibrium condition. There is no external influence, especially external field or see two very often as far as semiconductors are concerned, we consider two cases. One is equilibrium is disturbed by two things. One is the electric field, other one is the optical radiation, because uh, this optical radiation can be, or the electromagnetic radiation can be absorbed by, that is what you do in optoelectronic devices. It can absorb, photons can be absorbed by the semiconductors and they can liberate electrons and holes, so it can disturb the equilibrium. Of course magnetic field also can influence, but when very often for most of the electronic applications we use only these, either electric field is applied or the optical radiations or electromagnetic radiations are allowed to shine on the semiconductors. That way you can disturb the equilibrium. So now the problem is, the when you are operating the device or when you are using the device, it is a non-equilibrium condition. So equilibrium is disturbed. So that means you have a external field applied. So now such situations, how will I know the carrier concentration? Because without knowing the carrier concentration, I cannot find the current. So that is one issue we need to address. Now, I said, do you think that electric field is required for diffusion current? Is it a requirement for getting diffusion current?
Sir, I think for aligning the carriers.
No. What for? Like, is it? See, when we say we need carrier concentration, or the concentration gradient only is required for the current in, as far as the diffusion current is concerned, and PN junction are based on diffusion current, then what is the role of electric field? There also in PN junction devices also you apply the electric field. So what for the electric field is applied? If it is purely diffusion, why it is the electric field is required? Yeah, any idea? You always apply an electric field, no? Without application, you don't operate the device. Almost all PN junction devices, whether it is a diode or transistor, you apply the bias. Then why it is necessary to apply the electric field in a PN junction device? Even though we say that right from the beginning, I am saying it is a diffusion current based device. What is the role of electric field in a PN junction device? Yeah, any answer? Yes. Hello.
No answer, sir. No answer, sir.
Okay.
Don't.
Now I'll be taking up this issue later on. I'm not discussing right now because I need some figures, etc. So I'll be discussing it. So this is one thing, but we should keep that thing in mind. What is the role of electric field in a PN junction devices or in a diffusion current based devices, that we need to understand. So our first issue is finding out the carrier concentration under non-equilibrium condition. That is the first thing we need to address for getting the current. So in the equilibrium case, Fermi-Dirac statistics and or simplified form of Maxwell's-Boltzmann statistics in the case of non-degenerate, because Fermi-Dirac is to be used for heavily doped. So, but we have seen that for moderately or lightly doped semiconductors, we can use Maxwell's-Boltzmann statistics for the and then of course the law of mass action. Using that we can find out that this I mentioned. Then the question is, what to do under non-equilibrium conditions. So here we'll see that again. I'm talking very general today. We will be we will develop some simple ways of finding out the carrier concentration under non-equilibrium conditions. We will be invoking, so very often mathematics comes to our rescue. So based, of course, mathematics based on certain physics uh, will will get a partial differential equation for the carrier concentration, and the solution of that partial differential equation will give me the carrier concentration at spatial variation. That is the approach which is used. There are various kind of physics can be involved, and the various kinds of partial differential equation is possible, and the solution of that partial differential equation should be giving me the carrier concentration and its spatial variation. That is what we should keep it in mind. The partial differential equation means it can be, because if you want to see the temporal change, that means with the time, that also should be incorporated. Other one is the spatial, other one is the temporal. With the time, how the carrier concentration varies, both things are important, because transient response of the device are also important. Yeah. So we would like to know both. So that is possible. So mathematics comes to our rescue. Then when we talk of mathematical equations, the solutions, there are two methods. One is analytical and other one is the numerical. Do you understand the difference between analytical and numerical? What is analytical method? Yeah. Have you heard of these terms? Analytical methods, analytical solution, etc. in solving this differential equation, etc. Hello.
Yes, sir.
Yeah. Have you heard this?
Yes, sir.
Yeah. What is analytical? What do you mean understand by analytical method?
Sir, in which we analyze something.
That always do. We always analyze something. Science is all about that, or data is all. So, what is the meaning in mathematics when you say analytical method?
Where we use lots of approximations.
It is possible, but what is a fundamental thing in analytical method? Of course, there will be approximations. Yeah, that is true, but then that is not the main thing actually. Any other thing? Approximation will be definitely there. See, actually, all these things are based on physics, so some approximation you will need to introduce actually. The fundamental thing in analytical method is you have standard solution. We say talk of standard solutions, because you have certain, see for example, x squared plus bx plus c. You have a standard solution for that is b squared minus 4ac, that formula. I mean, you know that, no? So similarly, there are partial differential equations also. Standard solutions are available, so you can solve the solution, these those equations uh, with those standard solutions. So that is the analytical method, and very accurately you can solve that. No issue in that. So such equations which are having standard solutions are known as linear equations. So they are normally analytical methods or techniques are used for solving linear equations. Whereas very often the reality is, unfortunately, real physics, when you introduce, you will get normally a non-linear equations actually. Non-linear equations means you cannot solve using analytical method. So how will you solve the non-linear equations? How can you solve non-linear equation? Yeah, anyway, or you cannot solve the non-linear equations at all. Have you heard of non-linear equations?
So by integration.
Yes, sir.
Integration, all partial differential equations are solved. Integration is not. Integration is a general technique for you have a. You have studied one full paper on this, the mathematical techniques in electron. What is the title of your first paper?
Transforms. Sir, mathematical techniques for electronics.
Now, what is mathematical techniques in electronics? So, okay. So, so that is
Using
what.
transforms.
No, not transforms. So general, this very generic name or very general name is there. Very general name is they are using iterative techniques. You have heard of
Okay.
Yes,
iteration?
sir.
What is the meaning
Yes,
of
Yes,
sir.
sir.
iterate? What is the meaning of iterative technique?
Sir, it is repeated for many
Well, how will you
iterations.
repeat? How will you repeat?
Um,
What will you? How? What is? Why? How can you repeat something? You're doing the same thing again and again, or some?
no, sir. The value of
Yeah,
I changes. It increases every time.
What? Which? How you go about it?
The with the help of past result, sir.
See, actually,
yes, sir.
you start with a seed. So guess value or a seed. You start with the guess value and then you go on converging to an answer. So this is iterative. And what is the factors on which this accuracy of iteration depends? One of the main factors. There are many other factors also. So you need to do more iteration or less iteration, which will be more accurate. So if one case you are doing 10 iteration, other guy is doing 100 iteration, which is more accurate.
100.
Yeah.
100
So statistically, you can see that higher the number of iterations you carry out, more accuracy. Of course, you define certain person accuracy and things like that. So you need. So the essential difference between analytical and iterative methods is you need a tremendous amount of time. So how you do it? Do you with can you do it with a pen and pencil, or how will you do iteration?
So, various programs are there,
Yeah, you
computer
use a
Yes,
computer.
programs.
sir.
The important thing is
Computer is
you take
necessary.
advantage of the computer there. So it will go on this that monotonous. Earlier, people were doing it actually by hand also because then it will take a lot of amount of time. It's not that computer is something which is, but then there are techniques available like you have Rangagutta, Newton Raphson, and all kinds of things. Of iterative techniques are available. There are a lot of techniques available, so you have to see which technique is suitable for a particular situation, which gives you faster convergence and things like that. But important thing we need to understand is these nonlinear equations generally can be solved using iterative techniques, and iterative techniques are generally known as numerical techniques because you start with a guess value. So such equations are known as numerical equations. So generally we cannot do it by hand, or it will take. I mean, today nobody try to do it because the computers are available. So you write a code and give it to the leave it to the computer. I told you, like my case, I was using a technique known as Monte Carlo technique for my thesis work. So it used to take overnight actually. So you start in the morning around 9 o'clock, and 24 hours run was necessary for some of those results. Actually, you can imagine because as we said earlier, more the iteration, the more accurate it is. So if you run 24 hours iterations, of course, computers were not that fast. Also, that was another problem. Today, it may not be requiring that much amount of time. So, but you see that there are various techniques, and depending upon the faster convergence, there are methods. But you have a branch of mathematics devoted to this, and most of the real life engineering problems are solved using numerical methods or numerical solutions. So that is why the importance of that first paper, where you know that various techniques are available. So for the given case, you'll have to take a particular technique, and that way you solve it. That is the idea of it. So you have both analytical for simple, just to get a general idea about the problem, you use analytical methods are seldom accurate, they are not very accurate, but you get an approximate idea. For example, we have seen that abrupt junction, again that is an approximation. It is not possible to have a solution like a practical situation. It is not. We'll see later on. Practically, there is no an abrupt junctions are possible. So, but then if you assume that it is abrupt, you can use analytical method and solve it. That is what we are going to do in our limited time. We will not be going into numerical methods, but when you go advanced level, one can use numerical methods for the PN junctions and solve the thing. So one thing is we need a partial differential equation to get the carrier concentration, and solution of that equation analytically or numerically will give me the carrier concentration and its spatial variation. So that is one thing I need to do. So this we already mentioned. Analytical techniques use, you can use hand calculation. The limit problem is approximate. So only thing is the equation will give you exact solution, because a lot of approximations are involved in developing the physics. So that way it has a severe limitation. If suppose you are launching a space shuttle or designing an airplane, you don't use this uh, analytical technique to design it. You will be using numerical method to solve it, because the accuracy is very important. Time is not a constraint, so that we should understand. So most of the practical engineering solutions comes through the numerical methods. But for the academic, for understanding things in a simple way, we use the analytical techniques. So you have this numerical methods have these convergence issues and all those things. It takes time, so you have to suitably select the technique and all those things. Anyway, I'll not go into those details. You are supposed to be have covered it in the first paper, so you can always revisit that paper and see all the things, different techniques. And it's very important as you go further in science or engineering. These things become very important. Yeah, to select a particular technique, etc. Now, okay, here, so the first thing is find out the carrier concentration and or the spatial. So that is first step. Second thing is we want to know the electric field or the potential distribution in a PN junction device. So now I can get the carrier concentration and temporal, and its temporal and spatial variation is with the temporal means transient variation with the time how it varies, and the spatial variation. I can formulate something and get it. Now the question is, can I find out the electric field and potential distribution using that? That is the next question. So here, Poisson equation come to our rescue. So if you recall, Poisson equation is a link between the charge density and the electric field potential, etc. We'll be discussing in detail later on about this. So you formulate the Poisson once you have the charge density available to you. So suppose a certain region you want to find out the electric field or the potential, you formulate the Poisson's equation, and you can formulate the Poisson's equation if I know the charge density in that region. So you apply the Poisson's equation, or formulate the Poisson equation in that particular region using the charge density, and then you solve the Poisson's equation and get the electric field and the potential with respect to the charge density. So this is another thing. So once I know the charge density, electric field, and the potential, your job is done. So this we will see that we get the IV current, IV relationship using these two. One is I will get the electric field and potential. First part is of course finding out the charge density or the concentration of charges, or its spatial variation or temporal variation. Second thing is using that I find out the Poisson's, formulate the Poisson's equation and solve it. Again, whatever we said about the first is applicable for Poisson's equation also. It can be linear, it can be non-linear, and things like that. So it can be solved analytically, or it can be solved numerically. So that is could be linear or non-linear. Again, analytical versus numerical techniques will be available for the Poisson's equation also. So these are the two things when to find out the IV relationship of the semiconductor or the device actually, because it's a non-equilibrium situation. This once the carrier concentration on, we can find currents in PN junction. So then we can like see the steady state versus steady state means when a large amount of time DC condition. Basically, steady state is the DC condition. Transient means the transient response, including the AC response. AC, of course, means the frequency response actually. Transient means time response. So that is, you can find out. Then you can find out under different bias conditions what are the things happening to this charge density and electric field, etc. So you can find out it under different bias conditions what is the change in the IV relation characteristics. So as far as the PN junction is concerned, you have three type of biases you can apply. We will be talking in terms of forward bias. When you have P and P region is connected to positive terminal of the battery, and N is connected to the negative side of the battery. So that is a forward bias condition. And opposite, if you do, it is reverse. And then under large voltages, especially when you have the reverse conditions with a large amount of voltage applied, where the breakdown conditions. So we will be discussing all these things. First, we formulate the an equation for finding out the carrier concentration and temporal variation. Then we formulate the Poisson's equation to find out the electric field wherever it exists and find out the potential and electric field. Then we see that under various conditions like forward and reverse and breakdown condition, what happens and what is the kind of IV relationship we get. So these are the things we will be doing in this section. So any questions? So this is all what we are going to. This is a summary of what we are going to do in this section. You got the point? So
Yes, sir.
Yes, sir.
we need to find out the carrier concentration. We need to find out the electric field and potential. So we have, of course, we will see that for finding out the carrier concentration, we will use a very simple technique, that is known as, or simple equation, which is known as the continuity equation. Solve the continuity equation, we get the carrier concentration, and then put it into your Poisson's equation and find out the electric field and the potential. So that way we can get the IV relationship. So that is what we are going to do. And then we will be bringing in special cases. You have the long base, short base conditions, and all those things. We will be. So this is basically the objective of this unit is to, because you have two basic active elements. One is your BJT, bipolar junction transistor. Other one is the MOSFET. BJT is based on diffusion current. So this section gives you the basic framework or the basic physics behind the BJT operation. So once we develop the PN junction theory, that will be applied to the BJT, and we will find out the features of the BJT. So that is the objective of this. And what we do here is this, what already I have explained. You find out the carrier concentration and spatial variation, and then using Poisson's equation and the carrier concentration, you find out the electric field, potential, etc. So that is what we will be doing in this. So any questions?
No, sir.
Okay. Okay then. Stop it here.
Thank you, sir.
Okay.
Thank you, sir. Thank you.